All right. This is everyone, correct? Am I missing anybody? Look to your right and left to see if your buddy's here next to you. We're doing teams. Right. All right. How's everybody doing? Good. Cool. So looking at where we're at with things today, going to go through and hopefully finish up with t-tests, although that's kind of an aspirational goal. So just in terms of timeline, if we don't finish up with t-tests today, that would then push that set back to give you all a little bit more time to sort of go through and do that. What I don't want to do is have you work through a set without having us have gone through and work through all examples and things like that. So CJ went through, took a look at your problem set 3s. CJ, any comments or anything like that you have for people on those?
It looked real good in general. I think the only thing that kind of stood out to me is, so when you guys are like describing things or in your interpretations, you want to make sure that you're including your test statistic in those. So like for the last problem set with Z, we're getting into T here, F, whatever it is. Just because when you're like writing manuscripts or whatever, when you're going to publish something, you're going to be including those in your results there. So it'll be good to practice including those stats in these interpretations for the class.
Yeah. CJ makes a good point. A lot of this seems like a lot of hassle and a lot of sort of incorporating things. But I think, again, at the end of the day, what I'm hoping is get you guys a solid foundation so that when you roll into writing manuscripts and theses and stuff like that, all this is kind of coming second nature in terms of interpretations and stuff. So, as you're going through, I'm trying to give you examples of sort of like write-ups and things like that. If you go through and look at some of the examples that are posted in the slides, I'm trying to work in, sort of give you ideas on how to work in test statistics and things like that without feeling super, super redundant in terms of reporting things. So just take a look at that again. Would remind everybody that that's not like a template, like, oh, I want you to like cut and paste and just swap out words. But you all have been really fantastic thus far in putting together your own interpretations and things. Again, I'm really impressed. I was actually thinking about this today. This always happens is we get down to about this point in the semester and we'll be a week or two behind or something like that. And people are asking me questions about when our midterm or our mid-semester or semester exam is going to come into play. I don't know. You guys are just really crushing this. Like, you're just really, really doing well. Honestly. If you guys keep at this pace, I would start to question what the purpose of a mid-semester exam would be if you guys are just going through and really sort of knocking these out of the park like you are. So just keep doing what you're doing. We're trying to keep this in flux, but we may get to a point where not rushing in terms of ANOVA and contrast and some of that stuff starts to make more sense than having you guys sweat through an exam. So just keep doing what you're doing. Again, I can't say enough how well you're doing with these problem sets. They're clean, they're organized, you're taking feedback and stuff like that. So keep after this. We'll just kind of monitor things, see how things are going, and take stuff from there. Does that sound all right? Thumbs up? Okay, cool. Questions about anything that we've gone over up to this point? Sort of where we're at in terms of t-tests. People have said, we last time we had gone through and covered single sample T's. People feeling comfortable with interpretations, how we're sort of going about with our single sample test. Everybody's happy with this. Okay, cool. Well then, so we had gone through, talked about different statistics. We've got our statement of our null, that we put out is sort of in words, and again, sort of the idea is to get you and keep you thinking about populations, and that our hypotheses tests are always concerned with populations. We're trying to infer something about a population, sort of working that in to trying to get your head in the right space with this piece. Statistical notation, got your confidence interval, your test statistic, your p-value. Again, encouraging to report these, particularly if you've got a p-value that's only going to like 3 decimal places, just report the decimal places. But if things start to get smaller than that, remember we're thinking about p as a continuous index of evidence against the null hypotheses, right? Telling us, assuming that we've met all our other assumptions, how incompatible these data are with the null hypotheses, and p equals 0.0009 is a very different number than p times 1.83 times 10 to the negative 33rd, right? And so using some exponential notation to go through and really highlight sort of the magnitude of difference here. Our effect size, right? This is our measure of the magnitude of an effect independent of sample size for the most part. And then our S values and our Bayes factor. Again, these being statistics that we're using to augment our interpretations and sort of give maybe a more intuitive sense of the extent to which these evidence or the data that we've got really are inconsistent with our null model. Okay, so we've got a write-up here. Again, you'll see where I'm going through and kind of working in test statistics here. One of the things that came up that I'll provide some feedback on is some of you, and this is a good job, went through and gave me a literal interpretation of P, right? Saying if we're doing like old school classic hypothesis testing, right, the probability of these data or the probability of the observed mean or something more extreme, assuming the null hypothesis is true, sort of blah, blah, blah. That's a good exercise. You don't need to worry about that too much in your write-ups. That's not a probability value that's oftentimes given or interpreted in sort of routine practice. It's good to know like literally what that p-value represents, but again, sort of framing it something more similar along the lines of what we've got here. So just thinking about that. And if you have questions about your write-up, come talk to me, talk to CJ and say, hey, is this sort of getting at sort of what we're looking to get at here? Okay. This is sort of what I would want for a write-up. So it's something to demonstrate that you really, really know the ins and outs and the nuance of a test like this. This is way too much for a publication. This is not something that you would write up for a publication. Your reviewer is going to tell you don't need 3 pages to discuss the results of a t-test, right? But this might be something, a kind of condensed version that would work sort of more along the lines of something we might write up for a publication, something that still is focusing on this interval estimate and sort of pulling in some important information, but something that's streamlined down a little bit with some of this. So make sure to go through and take a look. You'll see kind of the differences here. Okay. Also, Mr. T says anytime you're going through and taking a look at your stuff, always make sure to evaluate this. Are my results credible, right? You know your area, you know your data. Don't just trust a computer program because it spits something out at you. Make sure that you're going through and saying, does this make sense? Or have I made an error somewhere? Is there something that's messed up? So you just got to be vigilant to your data and make sure always giving that plausibility check. Okay. All right. So this is good, right? We've talked about z-tests. We've talked about t-statistics. Both of these tests are used to compare a sample, our sample data to some known some known population value or hypothesized population value. But our single sample z and our t still end up requiring more information than is generally sort of available to us in routine research. More commonly, what generally happens is we're interested in comparing the means of 2 or more samples drawn from populations with some unknown mean and variance. Okay. What we want to do is we want to say, let's say Erica is running a study where she has looking at a sort of theory-based mechanism and wants to see whether or not a control group is different on some measure than a second group that's gotten some sort of experimental manipulation, right? Now, Erica doesn't know what the true value of the control, everybody, the hypothetical population of everybody who could be in the control condition and everybody who could be in the experimental condition, particularly if she's got some sort of arbitrary scale that she's measuring these people on. Erica, you don't know what the population values are, right? And so we're sort of out of luck in terms of a Z or single sample T, because we need to have some hypothesized value, right? What we would normally do is we would want to say, okay, is the difference that we're seeing between group 1 and group 2 sufficiently different enough to start to infer that these are samples that are likely drawn from populations having different means? Okay, and if we see our observed difference is large enough relative to what we would expect just due to random variation, then we would likely to conclude that these data are incompatible with the null hypothesis that the samples were drawn from populations having some equal value. Okay, and so when we're doing this, this is where we start to get into our our independent samples T tests. Okay, independent sample T used to look at differences across two population means. All right. Now, sometimes these are real populations. Sometimes these are populations that are just out there in the world, say men and women, or folks from the U.S. versus folks from Brazil, or individuals with PTSD versus those without PTSD, right? But sometimes these populations are hypothetical populations, right? Going back to Erica's experimental study, the number of people who have been in Erica's control condition and in her experimental condition are just the people who've been through her study, right? But that's not what we're looking at. Again, we're thinking the hypothetical control population. Human beings, if they were to complete the control condition, what would their score be? Human beings, if they were to get the experimental manipulation, what that value would be. And what we want to do is test to see whether or not the data that we're getting is sufficiently different in order to conclude that these likely are different populations with different levels on whatever outcome we're looking at. Okay, so again, with our independent sample T, we're comparing means from two populations with unknown parameters for that whatever our outcome is, and again getting down to our most basic experimental design. Okay, so again, we're thinking about, we've got population A, probably hypothetical population A taught by method A, hypothetical population B taught by method B. We don't know what these values are, right? So there's no value I can stick in the null hypotheses like we do with our Z test or our single sample T. Well, what we can do is we can sample sort of this population. We can sample that population and then start to compare the two with a little bit of a variation on our test. Okay. Questions about this? Kind of making sense? Okay. So, with an independent sample t-test, our hypothesis, okay? Our null hypothesis, formally stated, is going to be that the difference between population 1 mean and population 2 mean is equal to 0, okay? You could write this as population mean 1 equals population mean 2, but that's not really what we're testing here. So again, remember that our null hypothesis test is always, almost always set to that some value is equal to 0. What we're really interested in is the difference in these population means, right? And if the difference in these population means is equal to 0, that means they have the same number, right? So this is going to be our null, right? And we're proposing that the difference between population means is 0, or alternatively stated a different way, you could say scores were likely drawn from populations having equal means, right? Our alternative hypothesis here is that population mean 1, the difference between population mean 1 and population mean 2 is not equal to 0, okay? Again, this is the hypothesis for our non-directional test. For our two-sided test, right? This could flip-flop. It could be bigger one way or bigger the other way. We're just saying that it's not 0. Remember, and that's with our hypotheses testing, that's almost always what we're testing. Is something's not 0, right? And so think about this when we're thinking about, and it's easy to get into interpretations, say there's a meaningful difference or a significant difference, or my test suggests that there's an important difference between these two things. Not really. Remember that all our hypothesis tests are doing is asking whether or not the difference is literally 0, right? Now, sometimes that might make a difference, but probably most of the time it doesn't. So just remember and sort of keeping this in your mind as we're going through and interpreting things. Okay. So again, the difference in population means is some non-zero value. The observed scores are unlikely to have occurred if means of their respective populations were equal. Okay. So if, let's say, men and women truly were identical on sort of something that we were measuring, right? The data that we're saying is very, very unlikely, right? If men and women had the same value, it's unlikely that we would get samples of this size that deviate by this much. And as a consequence, we're saying that these data are incompatible with our null hypotheses. We're going to reject the null and conclude that these samples were likely drawn from populations having different means. Okay. People feeling comfortable? I mean, it's a lot of repeat, the same type of logic, just with little variations, but just want to make sure we're all sort of comfortable with this. Good. Okay. All right. And again, big question here with our independent sample T's. Is the observed difference in scores between these two samples sufficiently large to start to conclude that they were drawn from populations with sort of unequal parameters?
Can I ask a question just to make sure I'm
clear?
For the independent sample, so for the single sample T, it's literally just like a single sample, like what we dealt with, like the IIP scores. And for this independent samples, it's two different ones, right?
Yep. We're going to have two groups. We're going to have this group. We're going to have this group. And again, you're going to have two different populations you're interested in comparing, right? With a single sample, what we're doing is we're saying, hey, we're comparing this sample that I've got, which represents some population, with some known parameter, right? Or some hypothesized parameter. So we're just working with one group. Independent sample T, we have two different groups of folks here. Other questions? All right. Assumptions of our independent sample T. These are going to be mostly similar to our single sample T, but one, we're going to assume that our outcome variable is continuous. Okay, we're going to assume that the observations in each sample are independent. All right, we're saying that if I've got Ari, Robert, Erica, and Natalie are my one group, Brittany, Rachel, Ali, and Riley are my second group. What I'm assuming is that observations among you all is just your own stuff. It's not influenced by anybody else. You're not related to one another. We always want to make sure that conceptually there's no dependencies in our assessment or our measurement here. Okay, we're going to assume the distribution of sample means for each population is normal. Okay, so Ali, if I'm saying the distribution of sample means for each population is normal, do I have strong assumptions about the observed data that I see in my sample?
Sorry, so if the sample means are normal, then...
The distribution of sample means are normal.
Yeah.
Yeah. So do I, with this test, do I have explicit assumptions about what the distribution of scores in my data look like?
It should be about normal.
Okay. And it's nice if they are, right? But if we're talking about the distribution of sample means, what are we talking about?
Like all the samples that are drawn from like a population and the means of those samples.
Sort of plotted out, yeah. And under what two circumstances does the distribution of sample means start to become normal?
If the population is normal.
Population is normal?
Sample sizes are large enough.
Sample sizes are large.
30.
Yeah. So again, when we're going through, we're always going to screen our data because we want to know what's going on with our stuff. But we can still have pretty ugly looking observed scores. Our distributions can be kind of non-normal, but it still isn't a technical violation of my underlying assumptions, right? Because even if I have if I'm measuring Rachel self-harm, right? Probably has a skewed distribution, right? Frequency of self-harm in the past month or something like that, right? That's probably not a normal distribution. It's probably not a normal distribution in the population, right? But if you've got samples of, say 50. Let's say you're looking at some mood induction across people who self-injure, right? And so you've got sort of, let's say a treatment, right? An intervention. You've got a control group and an experimental group, probably. And if your outcome is occasions of self-harm, it's problematic. It's not continuous. It's a count variable. It gets into a whole bunch of stuff. But probably you're going to see a skewed distribution there. But as long as you have reasonably sized cells, that's technically not an assumption of your independent sample T, right? Because even though your observed scores are going to be pretty skewed, right? As long as you've got a reasonable size sample, we would expect the distribution of sample means, even though that the population distribution is skewed, the distribution of sample means is going to be normal as long as we're sampling reasonably large samples, right? And so that's what we're concerned about. We want to go through and note if our data are skewed. And if it starts to get crazy with real intense extreme values, then that starts to become a problem. But even if we're screening, we're saying, hey, my data are non-normal, that doesn't necessarily disqualify us or count as a violation of my independent sample t-test. Okay, so really, really important to remember, and something that people don't often recognize. The underlying assumption has to do with the distribution of sample means, not the observed scores. Okay. Now, the one thing we're going to add with our independent sample T is this homogeneity of variance assumption. What we're doing is we're assuming, in order for everybody to be throwing the disc that's the same size and the same shape and using the same sort of number of sort of space to go through and their wind up and their throw and stuff like that, in order for this to work correctly, independent sample t-test assumes that our populations have equal variance. Okay, that's suggesting that the samples that we've pulled from population A and population B, those populations on whatever I'm measuring have equal variance. Okay, now if they don't, that starts to impact things, right? It's a violation of assumptions, and now the distribution of my test statistic doesn't fall along the expected distribution that is assumed. And as soon as I've got a distribution that I don't know how it's a test statistic where the distribution is uncleared, then I start to run into problems with inference, right? So one of the things that we add into the independent sample t-test is we're assuming that the two populations which I'm sampling from have equal variance, okay? And this starts to be a big, big consideration. Homogeneity of variance is going to be something that we're going to be thinking about from here on out through ANOVA, through most of the stuff we do, in sort of thinking about our decision tree. What decisions do I make in terms of procedures to select and things like that, okay? Questions about homogeneity of variance? People kind of get a sense for what we're looking at here. And we'll get into this in sort of a little bit more as we work down. Okay. All right. So these are our formal, like our statistical assumptions. Some informal assumptions, again, assuming that our data don't contain extreme values that's going to start dragging around our mean, right? Particularly, I'm going to be more concerned about this if I have small samples. If I have small samples and I'm measuring something that doesn't have a large cap or a sort of a solid cap, I can start to get values that start dragging my mean around. Anytime I would add or subtract a mean, add or subtract an observation, and it starts to noticeably change the mean value for my sample, that's an indicator that you got a problem with this stuff. Okay. We're also going to assume equal sample size across groups. Now, this isn't a formal assumption, but it's sort of kind of worked in there. We run into problems as soon as we start to get largely discrepant samples and need to start thinking about making some alterations in order to address some of this stuff. Okay. So that, and then our auxiliary hypotheses. Remember that our whole foundation of our null hypotheses testing is assuming certain things about how we've collected the data, right? So it has nothing to do with the actual observed scores that we're seeing. It's having to do with the methodology, right? Because all of these tests were developed in a vacuum, in a theoretically perfect experiment where our sample is representative, our sample is randomly selected, I don't have violations of my distributional assumptions, my hypotheses were generated prior to the evaluation of my data, I've got a correct model, everything that needs to be in the model is included, nothing that doesn't need to be in there isn't included, my measures are valid, my measures are collected without error, right? These are all things that we never live up to, ever, right? And it would be reasonable to expect us to, right? But just recognizing that our test was developed and our test is perfectly valid when all of these things are true, but as soon as we start losing this stuff, it starts to degrade our inference and how we're sort of in the confidence that we can put in our assumption or our interpretations. People comfortable with this? All right. So, formula for our independent sample t-test, right? And we're calculating our test statistic, our t here. We're going to take mean of sample, or sample 1 mean minus sample 2 mean, and technically with our independent sample t, we've got we're going to subtract that difference from whatever difference we expect in the population mean. But to this point, Natalie, what are we expecting the population means to differ, or what's the difference score we're expecting for the population means? Under the null hypothesis.
Could you repeat the question? I'm sorry.
Yeah. So under the null hypotheses, what difference am I expecting between population mean 1 and population mean 2?
No difference.
Yeah, 0, right? And so if we've got a 0 difference, we don't need to subtract 0 from the end of something. I mean, you can if you want to, but it's so that we can go through and ignore that if we're if under the null we're postulating no difference between population 1 and population 2, which is what we're almost always doing. Okay, so we've got our observed difference between our sample means over the top of a standard error estimate. Okay, and again, for any means-based statistic, is we're always going to have observed difference, the difference that we see over a standard error. And someone give me a conceptual definition of standard error. Erica, can you tell me what standard error is?
It's the standard deviation of sampling distribution.
Fantastic. Absolutely, right? Standard deviation of my sampling distribution, or how much across repeated samples I would expect, sort of whatever I'm measuring to jump around, right? And so again, what we've got is the observed difference that we're seeing over how much we would expect it to jump around just based on random variation. And if the difference that we're seeing is much greater than what we would expect just based on random variation, we're going to have a large test statistic more likely to reject the null hypotheses here. Okay. Now, down here, our standard error starts to change a little bit for our independent sample t-test. Our standard error is this. Our standard error we're calculating here is the standard error of the difference in sample means. Okay, this is our expected difference in the means across samples, assuming the null is true. Again, our standard error here is telling us how well we would expect the difference in mean 1 and mean 2 from our samples to estimate our population difference. Okay, but what happens with our independent sample t-test, because we're looking at the standard error of a difference score, right? And so what ends up happening is we end up with two sources of error now, whereas with the single sample test, we were just working with one sample, right? And so we only had one source of potential error. When we switch over to our independent sample test, now we're estimating mean 1. So Riley, I'm estimating sort of my sample mean for my group 1 is estimating my population for group 1, whatever it was pulled from, or population A, let's call it, right? So I've got sample A representing the mean of population A. Do I think that my sample mean is exactly identical to the population mean? No, I don't, right? And then I've got sample B, right, which represents population B. Do I think sample B is going to equally represent population B? No. Nope. So I've got two sources of error. I got potential error in my measurement of population A and my potential error of population B. And so what happens is the estimate of our standard error needs to take into account both sources of potential error, okay? And so what this ends up doing is it ends up being an additive function of my two errors here. So the calculation of my standard error for my independent sample t-test is going to be the square root of variance from sample 1 over the size of sample 1 plus the variance from sample 2 over the size of sample 2. Okay, so we've got two error components in there that we're taking into account. Okay, now relative to our single sample test that only took one source of error into account, what were the consequences then for my standard error for my independent sample t relative to my single sample t? What do you think, Rachel?
Maybe bigger.
Yeah, it's going to be bigger, right? It's always going to be bigger. And this is one of the things that makes our independent sample t, for example, have less power than for a paired sample t, which is only taking in one source of error, right? And if we think about this starts to make sense. And again, anytime I'm trying to understand something, I want to understand at a conceptual level sort of why this is, and not just accept that it is, right? So let's say that we have two populations that we're working with, right? We've got population 1 here in the blue, and then we've got population 2 here in the red, right? And so my question here, the concern is, what's the possible range of any two randomly selected scores that I could take from population 1 and population 2, okay? So population 1 in blue here has a range from the minimum score is 25, the max score is 95. Population 2, minimum score is 15, max score is 65, okay? And so if I'm saying, what is the most extreme difference I could get from a randomly selected score from these two populations? Well, in the first extreme, I could get, let's say I randomly picked the max person or the highest score in population 1, which is going to be 95. And I also happen to pick the lowest score in population 2, which happened to be 15. Okay? And so the difference between the max difference in these two scores is going to be the observation from population 1 is 80 points higher than population 2. Okay? But in the other direction, I could also pick the largest score in population 2, which is going to be, instead of going population 1 first, instead of picking the largest score in population 1, I pick the lowest score in population 1. So I get a population, my score representing population 1 is negative 25. And then I go to sample a person from population 2, and I get the max score in population 2, which is a value of 65, right? And so what I get here in my first scenario, I get my observation from population 1 being 80 points higher than my score from population 2. But if things switch around, I could find that my person, my person from population 1 is 40 points lower than population 2. Okay? And so if I go through and plot this on a timeline, or excuse me, on a number line, for any two randomly selected scores from population 1 and population 2, I could find that population 1 is 40 points lower to 80 points higher than my score that I've drawn from population 2. Okay, so this gives me the possible range of different scores I could get from a single sample is a max of 120 point swing. Okay, and consequently, if I take the range of population 1 and the range of population 2, add them up, I get the same number. Okay, so again, what we're looking at here is recognizing that if I've got, and you can think about this instead of, so here we're talking about a population and pulling individually randomly selected scores, but we could also think about these two things as being sampling distributions, right? I could get the max value from my sample, the max value of a sample, the highest mean from a sample of a certain size from population 1, and contrast that with the lowest possible mean of a sample of a given size I can get from population 2, and it's going to make it look like sample 1 or population 1 is massively larger than population 2, right? But I could easily switch this around. I could get the max value from population 2 and the min value from population 1, and now all of a sudden it looks like population 2 is way, way bigger than population 1. So we've got a huge swing here. And so with our independent sample tests, what we need to do is calculate and account for the fact that we can have error going through in both of these. Now, in either one of these situations, the value that we've selected for each population isn't representative. Is it the most likely? Nope. But is it possible? Yep. And so what we need to do with this when we're calculating our standard error is account for this. And so when we're calculating the standard error, the mean, or the standard error, the difference in means for our independent sample test, what we need to do is we need to account for variability in sample 1, variability in sample 2. This is going to give me a larger standard error on average than for another test, but it's just greater uncertainty because we've added more samples into the mix. Questions on this? Are people kind of generally getting the idea of sort of what's going into our standard error here for these tests? Okay. All right. So we run into a problem though with applied statistics. Okay. What happens if our samples are different sizes? Okay. We're assuming sort of informal assumption is, and sort of when whoever was putting together t-tests is like, okay, we're sort of thinking about generally most of our statistics or a lot of our sort of classic statistics were created with sort of an experimental approach in mind, right? So again, Ari, if you're running an experiment and you're randomizing people to studies, you can say, well, or to conditions, you can say, well, I'm going to have 20 people in this group and 20 people in this group, because I get to pick how big the groups are, right? But sometimes that doesn't work out, and our groups are different just because we didn't have people come in or sort of lose data or something like that. If you're clinical folks where I can't randomly assign people to PTSD or self-harm or things along those lines, the people who I get is the people who I get, right? And so it's very, very rare, even in experimental studies, to have exactly the same sample size, right? We generally get closer in a lot of experimental studies, but there's almost always going to be some difference, okay? And so let's say, for example, I've got a sample 1 is got 10 people, sample 2 has 30 people, right? What we know is that our large samples have a better chance, or sort of are going to provide a better estimate of our target population parameter than smaller samples. Robert, why is this?
No matter what, we're going to have some form of sampling error, so the larger it gets, the more representative of the population it will be.
Yeah, on average, right? The larger the sample I have, the more observations I'm collecting from the sample, and on average, in general, assuming all things equal, I'm going to assume that my larger sample is going to be more precise than my smaller sample, okay? But if I have unequal samples, I've got population 1, my sample from population 1, my sample from population 2, and they're not equal, what I'm worried is that so I've got a difference in precision in my two estimates, okay? Now, my homogeneity of variance assumption for independent sample t-test says that I'm assuming that population A and population B have equal variance, okay? So technically, from a theoretical standpoint, it doesn't matter because we're assuming that they come from equal, that my the populations for which my sample were drawn have equal variance, right? But in applied work, those sample variances are never going to be identical. They're always going to be a little bit different. And when we've got unequal sample sizes, what we're concerned about is this smaller sample is going to start to exert more of an influence on my standard error, even though it was pulled from fewer number of people and is going to be systematically less precise than the sample or than my larger sample, okay? So again, you could say, well, we're just going to go through and sort of average the variances, right? Or if we go through and we say, because here we're just taking my variance here, dividing it by sample size, variance here, dividing it by the sample size. The problem is that if I have wildly different sample sizes, this estimate of my population variance might be much, much less precise than this one here, okay? And so what we're concerned about is that smaller sample having undue influence on my estimate of what the total variability in these populations are. So what I'm going to do almost always is going to go through and I'm going to first calculate, before I calculate my standard error, I'm going to calculate a pooled variance estimate. Okay, and my pooled variance estimate is going to give me a weighted average of my sample variances. Okay, so my pooled variance here is going to be number of people in sample 1 minus 1, multiply that by my sample variance, plus number of people in sample 2 minus 1 times my sample variance and populate, or my variance of sample 2 over the top of number of people in sample 1, number of people in sample 2 minus 2. Natalie, do you have a question? Oh, okay, sorry. I just caused you. It looked like you were doing the version of the to take your glasses off, like you're going. Back, this is garbage. It doesn't make sense. But okay, so people understand kind of what we're doing here. Okay, and what ends up happening then is that if I've got wildly different sample sizes, the sample, because again, the assumption of my test is that population 1 and population 2 have equal variances, right? But at the end of the day, I have to get some estimate of what that variance is. I'm saying that they're the same across the populations, but I have to get a number that says, here's my population variance, right? So if I'm doing that, what I want to do is I want to give the sample with larger, that has more people in it, I want to give that more weight than the sample with less people, because I'm assuming the sample with more people is a more precise estimate, right? And so here, what we've done is we've gone through and we've weighted based on sample size in generating our estimate of our population variance. Okay. Now note here, and sort of scribble this and circle it in sort of big red ink, that this is the formula for your pooled variance, not your pooled standard deviation. Okay. If you plug standard deviations into this, you're going to get something that's off. Okay. Because the average of two standard the average of two variances, if you take that pooled variance and take the square root of that, that number is not going to equal the weighted average of the two standard deviations. Okay, when we're running statistics, always wanting to be working with variance. If we sort of with this type of stuff, if we need to combine things, we're going to average that variance. We're going to pool the variance, and then if we need a pooled standard deviation, we're going to just take the square root of the pooled variance. Okay, don't try and use this don't try and plug in a standard deviation and say, oh, I created a pooled standard deviation. Mathematically, they're not equal numbers. They're going to be off. So just make sure that you're always using your variance. And then once you've got your pooled variance, if you need a standard deviation estimate, just take the square root of that. Okay. So our final formula for an independent sample t-test is going to be mean 1, sample mean 1 minus sample mean 2 minus population 1 mean 1, population mean 2, although that's going to be 0, so we can cross that out, right? We don't have to worry about that. Over our standard estimate of our standard error, right? And so our estimate of our standard error, what we're going to do is we're going to take our standard error formula here, where we would take the variance of sample 1 over the size of sample 1, variance of sample 2 over the size of sample 2. What we're going to do when we're calculating this is we're going to instead substitute the pooled variance, right? We're going to take our pooled variance divided by the size of sample 1, pooled variance divided by the size of sample 2, because again, the assumption of my test is that these populations have equal variance. And so what I want to do is get my best estimate of what that variance is. And so what I do is I create my pooled variance and then just divide that pooled variance by the size of this sample, pooled variance by the size of that sample, take the square root of that. That's going to give me my standard error. Okay. And then my degrees of freedom for my independent sample test is going to be my total sample with the sum of sample 1 and sample 2 minus 2. Okay, because we've lost 2 degrees of freedom. Remember, with our independent sample test, we lose a degree of freedom when we're going through and we're calculating the variance, right? But here, because we're calculating 2 variances, we lose 2 degrees of freedom, and so it's going to be a total of our sample sample 1 and sample 2 put together, -2 for our degrees of freedom here. Questions on where we've gotten up to this point? Okay, so again, these tests are it's the same kind of song and dance as we did with our independent samples. It's just we're just kind of sort of building on this as we're moving forward. All right, and again, why is it useful to know degrees of freedom in analyses? Okay, always, whenever you're reading a paper, right? If you're sort of up to speed with things, you know what the degrees of freedom should be with any test, right? And so if you start to see degrees of freedom sort of jumping around and stuff like that, you're solving a mystery here because you know that it looks there's likely that the samples that they're using are shifting sort of a little bit from test to test, which probably shouldn't be the case if they haven't told you explicitly, oh, hey, we're missing data and things along these lines. So knowing degrees of freedom and how those degrees of freedom relate to your statistical tests starts to become important information when you're going through and evaluating research and literature out there. It's something that flies under the radar for a lot of people, but if you're sharp and paying attention, you say, oh, it looks like there's something funky going on, right? Because if I don't know what the degrees of freedom are, if I don't know how many people are in the sample, then I don't know what the distribution of distribution of that test statistic is, right? And if I don't know the distribution, what do we call that? It comes around, right? Like eventually it won't be funny anymore, but then like I've got a Will Ferrell podcast I'll send you one. All right, cool. Other thing we want to think about in terms of our independent sample t-tests, okay? We're going to use and calculate our effect sizes a little bit differently. With our single sample t, there's really sort of the options. Our options for effect sizes are going to be kind of limited, right? There's only so many things we can work with. When we get into our independent sample t, there's a number of different metrics that you could use, and it's going to be up to you to determine which one of these is going to be the best for what I'm trying to communicate, given my sample, given my data, so on and so forth. Okay. So once again, raw difference in my means can be a meaningful meaningful measure of effect, right? Particularly if my outcome is something that has sort of intrinsic meaning. Okay. So Riley, let's say I'm looking at the impact of sports psychology work on sort of throwers' performance or something like that, right? And so I've got a group of throwers who are sort of practicing as usual, and then a group who's sort of working with a sports psychologist who's sort of enhanced sort of performance training, motivation, things like that, right? And what I could do is then I could record the sort of throws for my group A, who's not using a sports psychologist, group B, who's using a sports psychologist, right? Probably for people who do this, if I were to say the difference in my group that's working with sports psychologists are on average throwing 3 feet farther than people who aren't. Is that a big difference?
I would say not.
So not very big. Okay. What if I say it was a 15-foot difference?
Yeah, that's pretty big.
Okay. So what I'm doing is I'm running a study, but my outcome is something that has intrinsic meaning, maybe not to everybody, but at least to sort of people who sort of work with this. So you can say, oh, wow, that's a big difference, or that's pretty minor and sort of not all that terribly impressive, right? Same thing if I'm looking at my outcome is, say, money or something like that. Or, Rachel, going back to if you're looking at self-harm, right, number of occurrences of self-harm over a month or something like that. I mean, if I see a reduction in sort of 5 episodes or something like that, I might be like, that's pretty big effect or something along those lines, right? So just the raw difference can be a meaningful metric of sort of our effect size or the impact of whatever we're doing, okay? But a lot of times we're not. A lot of times, probably most of the time, right, what we're doing is we're using some arbitrary outcome. It's a measure that we've put together that might have questionable validity. The scores don't hold intrinsic meaning, right? Brittany, if I said sort of the difference between people in extroversion is there's a 7-point difference on this extroversion measure across groups 1 and groups 2. Does that mean anything to you?
Not unless I know the scale.
Yeah. Not unless you know the scale, right? And so for these cases, which is probably the majority of stuff that we do, raw difference isn't going to be a meaningful metric, right? So what we can do is we can fall back on our Cohen's d. Our Cohen's d is just going to be the difference in sample 1 and sample 2 over some estimate of standard deviation, okay? Now, what's the problem with saying, oh, we're just going to take this over some estimate of standard deviation given our independent sample t-test? What do you think, Robert?
Because you're taking the standard deviation of that sample, and it wouldn't necessarily be indicative of the population entirely.
Well, I'm hoping that it is, right? So it's my best guess. It's what I've got to work with. But how many standard deviations do I have how many standard deviations am I dealing with in an independent sample t-test? How many standard deviation estimates do I have?
Oh, you only have one because you're only working with one sample.
In an independent sample test? How many samples do I have in an independent sample t-test?
Oh, sorry, 2 samples.
2, right? And so the question is Cohen's original formula for our independent sample t-test just says the difference in sample 1, sample 2 over a standard deviation estimate. And the question is then for applied settings, well, which one do I use? Now, Cohen would say, well, we're assuming that the population variances are equal, so who cares? Pick, right? Problem is Allie, what sort of given math, what standard deviation might I be tempted to choose in terms of what I would like to see in terms of my effect size?
Probably the one that has less big standard deviation.
Yeah. I'm going to be tempted to use a smaller standard deviation, right? And what can start to happen, particularly if I have small samples and I got a lot of variability here, it can start to change my my effect size around quite a bit. Okay, so classic Cohen's d doesn't give us a specification on which standard deviation estimate to use. It just says the difference over the standard deviation estimate, which again gives us a metric that we interpret as in standard deviation units, sort of change or difference or things along those lines, right? But we'd like a little bit more guidance, and so some different metrics that have been developed. Glass's delta, okay? Glass's delta is saying what we want to do is we want to take mean 1 minus mean 2 over the standard deviation of a control group, okay? So going back to sort of experimental folks, Ari, if you're going through and you're running a study looking at spatial awareness, right? And you've got people coming in and you're just measuring their spatial awareness, and then you've got an experimental condition that's getting some sort of intervention or some sort of thing that you are hoping will boost spatial awareness or enhance spatial awareness. What I might do in terms of after I go through and calculate my test statistic, I might say, well, what I'm going to do is I'm going to go through and take this difference, and I'm going to use the standard deviation of my control group as the standardizer. The idea being that this is the control group. This is just sort of the world as it exists at baseline. What this can do is it can provide a nice, maybe potentially more interpretable effect size, because what I'm doing is I'm just looking at standard deviation difference sort of in sort of the world as we would expect it. Okay. Same thing, Natalie. Let's say you're running an intervention on assault prevention, right? And you've got population or sort of big sample where that didn't receive the intervention, sample that did receive the intervention, right? What you could say is, well, I've gone through and I'm going to create Glass's delta or calculate Glass's delta, and I get an effect size of, let's say 1.1, right? You got a big effect. You sort of had a pretty big, pretty successful intervention. You can say, well, what we see is that we're seeing about a little over a standard deviation reduction in occurrence of sexual assault based on variability that we would see in the normal population, right? Because we're assuming that the standard deviation of the control group is variability that we would just normally see. Okay, so if we've got a situation where we've got a good control group, Glass's delta is a nice metric because that variability that we're using to standardize is the variability that we would expect to see just in the population as it exists without fooling around with it. Okay, so this is nice, but where do we start to run into problems with Glass's delta? Conceptually, I guess, from a methodological standpoint.
When you don't have a control group?
Yeah. What if I don't have a control group, right? What if I'm looking at, sort of say, differences across decision-making or social processes in different sort of racial ethnic groups or something like that, or different minority communities or things along those lines, right? And I'm sort of comparing things like, who's my control group? Like, I don't know that I have a control group where this is sort of the standard at which all other folks should be judged, right? Or maybe I'm running a comparison against a couple of different treatments or manipulations, and there's no real control group because I'm doing stuff with everybody. At that point, Glass's delta starts to become a little bit tricky, okay? So what we can do, and what we'll often do, and if this is generally what we see, is something that is often, a statistic often known as Hedges G. This is the difference between sample 1 and sample 2 over the pooled standard deviation, okay? Now remember, pooled standard deviation, you're first calculating your pooled variance and then taking the square root of that pooled variance to get your pooled standard deviation. But essentially we're saying what we're going to do is we're going to take the observed difference and we're going to use the weighted average of the variance of my two samples and use that as my standardizer. Okay, this kind of splits the difference. It's saying so we're taking variability in both samples into consideration when we're going through and calculating my effect size. Sometimes, you know, you can there's some guys Glass's delta is probably going to be sort of a more intuitive effect size, but you rarely get in trouble using Hedges G. Okay. Problem is, what we see, and sort of people have been in the 80s, so I started identified this, is that we start to see in very small samples effect sizes being wildly overestimated. Okay, so again, for you experimental folks, right? We think about back to like those classic like social psych, cognitive psych experiments, right? Where you're using samples of, 8 in this group and 7 in the other group or something like that, right? The problem with that is we know that systematically when you're working with very, very small samples, our effect size that we would get calculated with Hedges G, or any of these quite frankly, tend to be far, far larger than as we start to get a more stable sample, okay? And so if we go through and we plot this out and look at the average, or if we look at the behavior of Hedges G with increasing degrees of freedom or sort of increasing sample size, we see that this starts to go down as our sample gets bigger and bigger and bigger. We get down to something that's probably much closer to where that effect size should actually be, right? So in simulation data, if we've got a effect size of about 1, if I'm pulling from these populations with samples that are quite small, I'm concerned that Hedges G is going to overestimate my my population effect when I've got very small samples. Okay, and so with small samples, we have Hedges unbiased G. What we get is a correction for small sample bias. Okay, so what we're doing here is we're taking our Hedges G and we're just multiplying it by a correction factor. Correction factor is calculated as 1 minus 3 over 4 times sample 1 plus sample 2 minus 2 minus 1. Make sure your order of operations are correct here, otherwise you're going to trick that up. But what this starts to do, if we take a look at this carefully, so Erica, if you're looking at this correction factor, what happens to the correction factor as my samples start to get increasingly large. So as my samples get bigger and bigger, what happens to the denominator of this whole thing?
It also increases.
It also increases. And if I take 3 and divide that by an increasingly large number, what do I get?
A smaller and smaller number.
An increasingly smaller and smaller. And so functionally, what I've got is this correction factor is always going to be a decimal, right? Because I'm taking 1 minus something that's sort of increasingly large, right? But as my sample gets larger and larger and larger, what does this do to my correction factor? Erica?
It decreases the overall.
Yeah. Perfect. Yeah. I'm multiplying something by a number that's still a decimal, so it's still going to decrease my my hedges G, but it's going to start to decrease it by a smaller and smaller and smaller amount, right? So if I've got a really small sample, I'm getting a pretty big correction because what I'm doing is I'm multiplying G by a smaller decimal, but as my sample starts to get larger and larger and larger, I'm multiplying it by something that's functionally equivalent to almost 1, which is going to sort of not be much correction at all, okay? So again, when you would use or report unbiased G, you don't actually see unbiased G a whole lot. You probably should. That's probably because it's starting to get harder and harder to publish studies where, I'm working with sample sizes of 10 and 12 or things along those lines. But anytime we're working with data where we have noticeably small samples, it's worth calculating unbiased G, right? And if you got reasonably large samples, if you were to calculate hedges unbiased G, it's probably not going to make a difference. So then it really doesn't matter. But with really small samples, you'll notice an effect here. From secondary analyses, okay, again, with all the stuff that we're doing, you have all the information to calculate these things directly. So if you're working with your own data, these are the formulas that you should be using. But if I'm doing some secondary analyses, right? I'm reading a paper that Brittany has published, but Brittany didn't publish means or standard deviation, so I actually can't calculate these things directly. But she has reported sample sizes and test statistics. What I can do is I can get approximations for effect size based on that information. Which starts to become very valuable. If I'm reading papers and they haven't reported effect sizes, that's fine. I can go through and calculate probably something that's roughly equivalent to what I would have had if I would have had the actual descriptive data, right? But main take-home point here is always make sure that you're reporting in any of your stuff descriptive information. You're just doing people sort of down the road who love your research and want to sort of go through and look at it. You're just doing them a favor as we move forward with this. Okay. So questions about effect sizes for independent sample t-tests. Okay. So when you're going through and taking a look, what you need to do is say, okay, here's the data I have. This is the methodology. Sort of this is what I'm dealing with. Which one of these effect sizes is going to make the most intuitive sense, is going to be most useful for helping to communicate the magnitude of effects I'm finding in my data. All right, cool. Let's do this. Let's stop. Let's take a break. Let's come back let's try. I want to get through this stuff. Let's try and take a shorter break. Let's try and get back here at 3:20, and we'll jump into this first example here. Okay. Perfect. Cool. Anybody else have questions about anything? We kind of sort of moved through that pretty quickly. Anything that people sort of having trouble with or sort of not quite 100% on with, sort of thinking about independent sample t-tests, what they're doing, sort of how we sort of put them all together? Doing all right? Cool. All right. Oops. There we go. All right. So going to walk through kind of just a hand example here, just to get a sense for how we go through and calculate some of these statistics. So we got a situation where researchers are interested in school performance in students having viewed Sesame Street as children and those who did not. Scholastic performance in 10 high school students having viewed Sesame Street in childhood were compared to 10 students who had not. Students having watched the program had a mean grade of 93 with a sample variance of 22.2, while those with no exposure had a mean grade of 85. Okay, variance, sample variance 17.8. Okay, so what we want to do is we want to state the null hypotheses in a sentence. We want to report this using statistical notation, calculate a 95% confidence interval for the point estimate of not interpersonal difficulties, academic performance in the sample. Provide an index of the absolute magnitude of the difference in the sample. This is going to be our effect size. We're going to conduct a hypothesis test. We're going to report and interpret an S value, going to report and interpret a Bayes factor, and then we're going to pull it all together and sort of provide our conclusions and sort of inferences based on the stuff that we've gone through and done. Okay, so for parts 1 and 2, we're going to go through and get into that sort of when we get to the end of the slide, but let's start by calculating our 95% confidence interval. Okay, so if we're going through and taking a look, so we've got our folks who did not watch Sesame Street as kids. 10 people, mean of 85 in terms of their grade, standard or variance, sample variance 17.8. Our Sesame Street group, 10 people. Sorry about that. That's a mean value of 93, variance estimate of 22.2. Okay, so first thing what we're going to do is we're going to go through and calculate a pooled variance estimate. Okay. So we've got our pooled variance formula. Remember, sample 1 minus 1 multiplied by the sample variance, sample 2 minus 1 by the sample variance, all over sample 1 plus sample 2 minus 2. Okay. So here we've got 10 minus 1 times my sample variance plus 10 minus 1 sample variance, sample 1, sample 2 minus 2. If we run this all out, it's going to give us a value of 20. Okay. Now, question, did I need to calculate a pooled variance estimate here? Who's got a calculator with him? Robert, you got one? Okay. What if we take 22.2? What if we take the average of 22.2 and 17.8? What do we get? 20. Okay. Why could I just take the arithmetic average of my two variances in this problem?
It's because you have equal hands.
Yeah, my sample sizes are equal, right? And so this is the thing. I would generally recommend people to just use the pooled formula, just because it sort of gets you in the process of sort of getting familiar with pooled variance estimates and things like that. But if we do end up having equal sample sizes, just taking the mean is a easier, faster way to do that, right? So I'm fine. Now you do whatever you want. But the reason I just went through the pooled variance here is just to kind of show you what's going on. But really with this, because we've got identical sample sizes, we're assuming that both of these samples, that these two samples are estimating the corresponding population parameter with equal levels of precision. So you could take a shortcut here. This happens to be equal sample sizes. Okay, so we've got a pooled variance estimate. Okay, and what I want to do now, if you want to calculate a confidence interval, I need to get an estimate of my standard error. Okay, so my formula for standard error is going to be the square root of my pooled variance over sample 1 plus my pooled variance over sample 2. Okay, so that's easy enough to plug in. My pooled variance is 20. So I've got 20 divided by 10 plus 20 divided by 10, which gives me 4. Square root of 4 is 2. So for this, for this contrived sample, my standard error here is 2. Okay, and so thinking about standard error conceptually, right? what this is saying, I can think about this as the standard deviation of my sampling distribution of the difference in population means, right? So I would expect, on average, any two randomly selected samples of size 10 from these respective populations to sort of jump around by about 2 points, right? On average. That's not to say they can't sort of deviate. Or I would expect any randomly selected estimate of the difference between the two samples to be about 2 points away from the true population difference. Okay, so I've got my standard error. And so what you can do is then calculate my 95% confidence interval. So I've got 93 minus 85, which gives me 8, right? So I've got a difference of 8 points. I'm seeing that the students who had previously been exposed to Sesame Street in their youth are scoring about 8 points higher than our folks who weren't exposed to Sesame Street. And then I've got plus or minus. What's this value right here? Someone want to tell me? What do you think, Allie? Yeah. See, you knew the whole time. You just were freezing me out. And yeah, you're exactly right. This is just your T statistic. Okay. So again, if you go through your T table here, right? Brittany, how many degrees of freedom in this test?
9.
Okay. So it's an independent sample test. So how many degrees of freedom? How do we calculate degrees of freedom for our independent sample test?
Oh, do you add?
Yeah.
So it's 11.
Well, so how many people in sample 1?
Oh, it's 21.
Getting there. All right. So 10 people in sample 1.
10 in sample 1 and 10 in sample 2, right?
All right. And then so we take that minus 2.
Oh, it's 18.
18. There we go. 18.
It's still subtraction though, but
Yep.
it's 2 because you have 2. Okay.
There you go. Right. So if we go through and I take degrees of freedom, 18, and I go through in my t-test table, so it's down to a two-tailed test with 0.05 at alpha 0.05, 18 degrees of freedom, seeing that right here, well, is 2.101. Okay. So this is an easy one to use your t-table test to get that here. For other applications, what I will do is I've got just this Soper, I think is this Daniel Soper. So the critical value for T value, so I could put in 18 at probability alpha 0.05, and it's giving me 2.101, right? So if I've got weird off-brand, let's say I need, 62 degrees of freedom, that's not going to be on your table. I just calculate. So my critical T is going to be 1.2 here, right? So this is just, this Daniel Soper, sort of this free student T value calculator. It's just the one that I use. There's lots of them. You can go through and use whatever one you want. But that's where another way you can get that if you can't find the critical your degrees of freedom exactly on here, right? Because you get 29, 30, and then we jump to 40, 50, 100. You won't always be able to find that in tables. Okay, so got my critical value multiplied by my standard error. It's going to give me a confidence bound or interval estimate of 3.8 to 12.2. Okay. So, Natalie, can you give me a conceptual interpretation of this confidence interval?
Let me figure out 1 minute. So
data, and I might mess this up. So
No,
bear with
go
me.
for it.
The data is likely to lie between suddenly all information has left my brain, so bear with me. I'm so sorry.
No. So what is our best guess for the difference in GPA, or excuse me, in grades across students who have and have not been exposed to Sesame Street?
Our best guess would be between 3.8 and 12.2.
It would be so that in terms of ranging. But what's my very best guess?
Oh, like the point estimate?
Yeah, what's my point estimate for the difference here?
It would be between 17.8, well, 17.8 or 22.2, right?
Okay, so that's my variance. But if I'm looking at my means, what's
It means 85 and 95.
85 and 93, which is going to be how many points?
Sorry, what?
So my estimate for the no Sesame Street group is 85. My estimate for the Sesame Street group is 93. So what's my best guess for the difference between those two groups? How many points?
The best guess for the difference between the two groups would be the 3.8.
Okay. So what's 93 minus 85? What's our difference here?
It's
8. Okay. So based on the data that I've got, what's my best guess for the population difference in grades for kids who were previously exposed to Sesame Street versus those who were not? 8, right? Based on the data that I've got, my best guess is that those individuals who had been exposed to Sesame Street in childhood are averaging about 8 points higher in their grade than kids who were not previously exposed to Sesame Street, right? And that's my very best guess. On my sort of peak, that's right at the top, right? And so if you put a gun to my head and said, what is the difference, I would have to say 8. That's my best guess, right? But do I really think that it's actually 8 points? No, right? Because I know I'm going to have sampling error there, right? So I want to know, given the data that I have, what would be supported values? Like, what would be sort of, given the data that I found, what would be reasonable estimates of the true population difference here, right? And based on the confidence interval I've got, what's the low bound for the true difference across these populations? 3.8. And what's the higher bound?
12.2.
Okay. Natalie, is this a very precise confidence interval? Again, if we're thinking about sort of standard grades, right? Sort of 0 to 100 grades. Is this very precise?
Not super precise, but not
No.
too bad.
Yeah. Well, I mean, sort of we're guessing an 8-point difference in overall grade. But that could be anywhere from under a 4-point difference to a full sort of letter grade above, right? So again, we've got a pretty broad estimate. And why do we have a broad estimate here?
Because our sample size is pretty small.
Yeah. We've sampled 10 people who hadn't been exposed to Sesame Street kids, 10 people who did. We've got unreasonably small sample sizes for this contrived example, right? And that's why we've got a really large interval here, right? But remember, so our point estimate is always going to be our best guess. If we had to put everything we own on a number, we would put it on our point estimate knowing that we would lose all our money. But it's the best guess we have. We'll be wrong less by betting sort of our mean than we would be if we were to guess other things. But given the data that we've collected, any population estimates of the difference ranging anywhere from 3.8 to 12.2 are going to be estimates that are going to be supported by our data, sort of given how we've constructed this. Okay. People see how we're going through and interpreting this. It's a little bit different because we're talking about a difference as opposed to a mean. So we're doing a little bit of a shift there. But any questions about this? Okay. So we've got our confidence interval, our effect size, right? Now there's a number of different effect sizes that we could calculate for this for these data. We could do a raw mean, or a raw difference, and I mean, because we all have grown up since age 5 and sort of moving up, probably what that 0 to 100 grade looks like, and I know what 8 points is, right? If I said, hey, here's a study technique that will add 8 points to your overall grade, would you use that study technique? I would hope so. That's a big chunk of change, right? So 8-point difference, I can just see sort of just on the surface as that being pretty decent size, right? But what I could also do is I could calculate a Hedges G, okay? I could say, okay, what I'm going to do is I'm going to take the pooled standard deviation and I'm going to take the difference divided by my pooled standard deviation and get an estimate there, right? And so here, we're just taking sample 1 minus sample 2 gives me a difference of 8 divided by my pooled standard deviation. Now what I did is I took my pooled variance, which was 20, and then I just took the standard deviation of that, okay? Whenever we're working with a pooled standard deviation, you always want to make sure that you're calculating your pooled variance first and then working backwards from that. And if I do this, I get an effect size of 1.79. So what I could say here, and again, we're going to emphasize and sort of, I was going to say encourage, but that's not force. Force you all to give me practical, conceptual interpretations of your effect size. What I would do is I would look at this and I would say these data are suggesting that there's almost a 1.8 standard deviation increase in overall grade in individuals who have viewed Sesame Street, have been exposed to Sesame as children over those individuals who haven't. Okay, if I say that there's a 1.8 standard deviation increase, is that a big increase? Yeah, that's massive. That's huge, 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 right? And so I can say, okay, an 8-point difference, that's pretty big. But if I use it, put it in standard deviation terms, I've got about a 1.8 standard deviation increase in scores among kids who have been previously exposed to Sesame Street versus those who aren't. That's a big difference, okay? But I also have a sample size of 10 groups of 10, and I know that that's probably going to be, I'm worried that my Hedges G is going to be an overestimate. Okay, so what I might decide to do is I might decide to report Hedges unbiased G, and in this case that would probably be a good idea, right? So again, unbiased G, we're just taking my point estimate of G and then multiplying it by my corrective factor. If I do this, I've got 1 minus 3 over 4 times 18, right? Make sure that you get this order of operations correct, minus 1. So to go through and run that out, I get a Hedges unbiased G of 1.71. Okay. Rachel, does this make sense? Yeah, why is that?
Well, because you'd expect the one that's biased to be a larger, like an overestimation
Yep.
of your effect size.
Yep. And so we've seen actually a fairly decent shrinkage on that effect size because I'm using pretty small samples here, right? So given what I know about Hedges unbiased G and what it should do, that makes sense to me, right? It's shrinking this down. It's still a massive effect size, right? With unbiased G, I'm saying that based on the data I've collected, we're seeing about a 1.7 standard deviation increase in final score among kids who were previously exposed to Sesame Street relative to those who weren't. That's still really big. It's a correction. It's a bring down a little bit from before, but it's still really large. Okay. Or maybe I go through and I decide to calculate Glass's delta. Erica, can you give me a justification or an argument for why delta might be the best or a good effect size to report here?
I guess because the one that doesn't watch Sesame Street would be a control group.
I could think about it that way, and I think there would be a reasonable argument for that, right? If we think about a world without PBS and Sesame Street, that's just kind of the state of the affairs. We can think about, in this case, about Sesame Street as being an intervention, right? Or a manipulation or something like that. So folks just out there in the world not exposed to it, if we assume that people who do view Sesame Street as kids are in all other ways equal to those who don't, which is not a strong assumption, but we could say this is the state of affairs for kids who weren't exposed, and so we're going to use their variability as our standardizer, right? So I would say here, glasses delta. If I take the square root of the variance of my no Sesame Street group, take the square root of that, gives me the standard deviation for that sample. What I would say is there's these data are suggesting a 1.9, almost a 2 standard deviation unit increase in scores among individuals exposed to, having previously viewed Sesame Street in standard deviation units, sort of based on the control, right? Being people not exposed, right? So kind of incorporating that stuff in, okay? And so, honestly, any one of these would probably be reasonable. I probably like delta the best. Maybe. Unbiased G, probably sort of equally sort of defensible here. G, with a sample of this size, G is going to be a little bit inflated, so probably ought to sort of make a correction on this. But sort of what we would want to do is sort of think about what do I got and then make an argument for which one of these that you think is the most appropriate for the data. Questions about our effect sizes? All right. At this stage of the game, do we need much else? We kind of got everything we need, right? But because we don't get to play by the rules, we're going to go through, calculate our formal hypotheses, tests, and our p-values, and so on and so forth, right? So here, if I go and so my test statistic, my independent sample t-test, is going to be mean 1 minus mean 2 over my standard error, right? I've got 93 minus 85 over my standard error. Calculated that a long time ago. That's 2. Gives me a test statistic of 4. And then again, if I go to my p-value calculator, right, and I want to look at a p-value of 4 with degrees of freedom. Brittany, how many degrees of freedom? 18. Perfect. 18 degrees of freedom. Compute p. Unit value of 0.0008. Okay, so what I could do is I could report that as, normally I would report it as p less than 0.001, or I could report it p equals 0.001. That's probably close enough here, but for this example, we'll just report it to 4 decimal places here. Okay. Last thing we wanted to do, calculate my S value and my Bayes factor. Okay. Remember that our S value is going to be the absolute value of the natural log of our p-value over the natural log of 2. So if I go the natural log of 0.0008 over the natural log of 2, take the absolute value of that, I get a value of 10.29. And remember that our S values, those are rounded up to the nearest whole number, so or rounded to the nearest whole number, so I get a value of 10 here. For my Bayes factor is 1 over negative e times p times the natural log of p, okay, which gives me 1 over negative 2.718. Can someone tell me where I got 2.718? What is that? Do I think, Ari, do you know where I got 2.718? No. Anybody a math nerd? Allie, where did I get 2.718?
Could that be like, is that what you think it is in the population? Or like your guess for what the alternative hypothesis is?
Okay.
Like what it will be, the difference?
Okay, so your head's in the right place, right? With the Bayes factor, where sort of prior probabilities and stuff like that. That's actually not what this is getting at. So here, 2.718. This is, and that number actually gets sort of infinitely large. This is just base E. Okay, E is a constant. E is like pi or any other mathematical constant. If you, let me see here. I go scientific. If I, here, there's a little e. There's 2.718, sort of blah, 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 sort of goes on infinitely. Okay, e is just a constant. All right, the natural log, this is just base e. So if I take the natural log of that, I'm going to get 1, right? So e is just a mathematical constant that's helpful for or useful for a lot of things. Think of this as pi as anything else. So if this is a mathematical constant, Erica, will this number ever be different?
No.
Nope, it's always going to be the same just because this is e, right? So we've got e times 0.008 times the natural log of 0.0008 gives me a Bayes factor, if I just calculate it here, of 64.49. Okay. So people are seeing how I'm sort of going through making those calculations here. All right. So, results. Okay. What I've got here, remember, first what I needed to do is provide a statement of the null hypothesis in words. Now, sort of yours might sound a little bit different, but it could go something along the lines of mean grade of high school students exposed to Sesame Street and high school students not exposed to Sesame Street is equal across their respective populations. Okay, so you notice what I'm doing here is I'm identifying sort of my populations and sort of pulling this together, saying that they're equal, they're going to be the same. So you just want to be able to sort of state this that sort of draws reference to those populations. And this, again, is just my effort to always anchor you back that we're never talking about samples. We're always trying to infer something about some population of interest. Okay. So in statistical notation, my null population mean of Sesame Street exposed folks minus the population mean of not Sesame Street folks is going to be equal to 0. My alternate, that these two things are not equal to 0, it's some non-zero value. Here's my confidence interval we calculated. Here's my effect size. For most of our problems, I'm not going to have you calculate all possible effect sizes. I'm going to say, tell me which effect size you think is the best one to use, give me a justification, and then you're going to tell me what you chose and why, and then you're going to go through and calculate that. Okay. Here's my critical T, my actual test statistic, my p-value. If I wanted to keep this and report this in scientific notation, I report it 8.40 times 10 to the negative fourth, right? So I take that 1, 2, 3, 4. Actually, if we continued this on, there'd be 0.000840, right? So this is going to go on. This is just shortening this up some, okay? What I'll have you do eventually is, again, what I'm gonna have you create calculators for your S values and your Bayes factor. If I have a test statistic of 4 and a degrees of freedom of 18, my p-value calculated by Excel is going to be 0.0000840 or 8.398. So it just kind of gives you this. Also, your S value and your Bayes factor here, or your Bayes factor in particular, is going to be a little bit different than what we calculated by hand, just because it's more precise. Okay, this is why when I'm having you do this in class, I'm going to always ask you to tell me exactly what you use to calculate your Bayes factor, because it can start to jump around. It's hard for CJ and I to tell if you made an error somewhere, if you're just using a sort of more or less precise estimate. So, but we'll get into that. But here for this example, we just counted it by hand, so that's fine, or calculated by hand. So my S value was, 10. And so what I would say is the results of an independent sample t-test provide similar evidence against against equivalent performance in these populations as would observing 10 successive heads and tosses of a hypothesized fair coin. Okay, so Ari, I say, hey Ari, I got this fair coin. I call heads, you get tails. And I flip 10 heads in a row. How confident are you that I have a fair coin? Not at all. Okay. Ari's fallen somewhere between Erica and Robert here in terms of their confidence and sort of my scrupulosity. But again, 10 heads in a row is, it's starting to be pretty suspect, right? I could also, again, taking that p-value and putting it into something that makes some sense intuitively, right, as evidence against the null. With the Bayes factor, my Bayes factor is what we calculated here, 64.5. We could give an interpretation of this saying, based on the available data, the likelihood of greater academic performance among Sesame Street exposed high school students versus non-Sesame Street exposed students is at most 64.49 times that of equal academic performance. Is this starting to become pretty compelling? Yeah, right? If I go, let's see here, back up here, remember that in terms of thinking of our interpretive standards for Bayes factor, anything going from about 10 to 100 is pretty strong evidence, right? So if our Bayes factor is 61, it's falling in that sort of fairly strong evidence, right? So we're feeling pretty confident that what we've got here is pretty strong evidence against the null hypotheses. Again, assuming that everything else that we've done is kosher, right? So trying to tie this all together, because I'm going to have you're going to be pulling in and calculating a lot of information. Sort of the main idea is then here at the end to kind of pull this all together, right? Into something that makes some sense in terms of a conclusion about the question at hand. So we say high school students reporting exposure to Sesame Street in childhood demonstrate an 8-point increase in the average grade as compared to high school students with no exposure to the program. Okay, you give me the point estimate. I'm saying, okay, that's pretty big. The difference observed in these data is consistent with 1.7 standard deviation increase in performance relative to students with no exposure. Estimates of the population difference compatible with these data range from anywhere from 3.8 to 12.2 percentage points. Despite the small sample available for the study, results of an independent sample t-test provide relatively strong evidence of greater academic performance in students exposed to Sesame Street childhood. Listing out all of this, right? This is where CJ is talking about sort of making sure that your interpretations are pulling in those statistics. Again, at this stage of the game, do I need to talk about significance or anything like that? No, we're just forming this all on strength of evidence. How confident are we that the difference that we've found is pulling in, right? I don't have to fall back on p less than 0.05 or difference or significant difference or anything like that. I'm just saying it's sort of a pretty strong evidence, right? So what I would say is, although the methodology of the study requires additional scrutiny, right? Because there's probably other things that are going on in terms of children who are systematically exposed to educational television as children relative to those who are not, right, is probably not completely due to assess. There's a bunch of other stuff that needs to go on. We've got a small sample. There's a lot of questions we could have about this study, right? But we can say the current data suggests early exposure education programming could be associated with 2/5 of an overall letter grade increase, could be associated with 2/5 to over a full letter grade increase in average sort of exam scores, okay, or grades or whatever. Where did I get that 2/5 to over a full letter grade? How did I pull that in?
Is that you interpreting your confidence interval?
Yep. It's me putting my confidence interval into terms that's going to make some sense to people, right? So if I figure a letter grade is 10 points, right, so to standard scale. sort of 89 or 90 to 100, 80 to 90, 70 to 80, so on and so forth, right? If I take my low end of 3.8 and divide that by 10, I get a value of 0.38, right? Which is a little under 2/5. A fifth is 0.2. 2/5 is 0.4. And so what I'm doing is I'm just taking sort of this and thinking about this in a way, okay, what can I do? How can I frame this in a way that's going to make sense to people, right? So I'm saying that early data is suggesting that early education to programming anywhere associated from about a 2/5 to a full letter grade increase in performance relative to high schoolers who weren't previously exposed to educational programming. Again, thinking about the biggest and I think the trickiest thing about statistical analysis is communicating to people in a way that's going to make some sense and carry some weight, right? As opposed to just reporting numbers. It's easy to crunch out numbers and sort of throw things around. What sort of starts to get tricky and sort of builds on your proficiency as a researcher is able to take this and sort of say, hey, this is what this really means, right? So for these data, a lot of stuff going on with the study, right? Probably not the best methodology. I would like to see much larger samples and obviously controlling for a whole lot of other things, sort of home life and poverty and sort of access and sort of a ton of other things, right? But sort of at least given the data that we've got, sort of this is kind of what it's saying. Okay. Questions about how we've gone through taking all this stuff that we've calculated and kind of put it together into something that tells us not only that, academic performance in these two populations is likely to not be the same, but starting to put some magnitude and some interpretative qualities around that. So they're not just saying that there is a difference, but talking about how much of a difference and starting to think about what that might mean. Feeling all right with this?
I just have one question just to make sure that I understand.
Sure.
So the critical value on the part B comes from like your chart that you look up, and then the T18, so like T degrees of freedom is the one that we calculate.
Yep.
Right?
Yep.
Okay.
Yep. So one's just your test statistic, and the other one's your critical value. Honestly, as we start to get farther on, the critical value starts to make, you'll want to have that. You'll need it for some things. But again, from a classic sort of yes-no decision making, right, we'd have that critical value be, does our test statistic exceed that, yes or no, to make a sort of fail to reject decision. I'm encouraging us to still use more of a continuous evidence against the null approach, sort of using the p-value and sort of some alternate statistics to try and sort of give that some more intuitive sense. But I'm just throwing it up there to just give me completing my reporting here. All right. Cool. All right. One more problem to introduce before we run into our break. Okay. Our assumption underlying assumption of independent sample t-tests is that the variance in our respective populations is going to be equal. Okay. But what if it's not, right? What if I'm wanting to look at compare this pre-existing population to this pre-existing population, and whatever I'm measuring, the difference, there's not the same amount of variability, right? If I'm looking at folks with PTSD on quality of life and individuals without PTSD and quality of life, I might find a whole lot more variability in quality of life across people without PTSD than people with PTSD, right? I might expect a clinical sample to have pretty poor quality of life, and that's actually a pretty restricted range, versus quality of life in sort of people without PTSD is huge. Some people are really low, some people are really high, right? So what happens if I'm trying to go through and I want to run a t-test, but I have pretty good evidence that the variance is not equal, that I have a violation of that homogeneity of variance assumption? Well, the problem is that the sampling distribution of my test statistic, the sampling distribution of t, if I pull my means from populations that don't have equal variance, my test statistic, my t-value, or my t-statistic doesn't follow a standard t distribution. Okay, Rachel, what do we call it when we don't follow a standard known distribution? See, this is what I do. Everybody's anticipating the paranormal distribution, but I'm not going to give it to you this time. I'm not going to give it to you. Just keep you guessing, right? Because you never know when that paranormal distribution is going to pop out or when it's not. That's what makes it paranormal and scary, right? But that's essentially what we're worried about, right? As soon as we are pulling samples from populations that don't have equal variance, and I go through and I'm still going to calculate my test statistic, the problem is my test statistic that I've calculated no longer follows a known distribution. And if my test statistic doesn't follow a known distribution, now all of a sudden my confidence in the accuracy of my inference starts to be degraded, right? And this starts to become problematic. So this is obviously a huge limitation, and so we want to try and develop a workaround, and a couple of different sort of ways people have developed to try and deal with this. One is Behrens-Fisher approach, and so this is an older approach where what we do, instead of having a t distribution, we have a t prime distribution. Okay, and t prime is our test statistic that's calculated from when we're drawing samples from populations with unequal variance. Okay, and so what Behrens-Fisher did is they went through and they tabled the distribution or the sampling distribution of a set of t primes, but just for a specific number of distributions, right? And so this is generally not terribly helpful unless I know that sort of the t distribution that I'm pulling from falls into one of these ones that have already been tabled. So we don't usually worry about this. What's become used in routine practice is known as a Welch-Satterthwaite solution. And Welch-Satterthwaite assumes that the distribution of t prime falls along a legitimate t family. We just don't know what the degrees of freedom are, right? So I've gone through and I've calculated a test statistic, and I've pulled this using samples. I've calculated this using samples from populations with different variances. Welch-Satterthwaite assumes that the sampling distribution of my test statistic does follow a t distribution. We just don't know what t distribution it follows. Okay, it should be the distribution that is associated with the degrees of freedom in my sort of sample, but we know with a high violation of homogeneity variance it doesn't, right? So what we're assuming is that our t statistic still follows a t distribution. We just don't know which one. Okay, and so what we do with this is we estimate the degrees of freedom for our sampling distribution based on the variances that we've observed and the size of the sample in each group. And so what we'll see in SPSS and STATA and a number of things, our routine test of homogeneity of variance is known as the Levene's test. Okay, and what Levene's test for homogeneity of variance is doing is it's taking the observed score for everyone in the set, and it's replacing it with a deviation score from the mean. Right, this is either a sort of absolute deviation or for a squared deviation. And then what Levene's test is doing is it's constructing an independent sample t-test using the mean deviation score, right? So sample 1, we get a deviation from the mean. Sample 2, we get an absolute deviation from the mean, sort of above and below. We take the absolute value of that. And if we do see equal variability across both groups, what should that average deviation score be in both of my samples? Should be the same, right? If on average both scores are deviating about 5 from their sample mean, then my mean deviation score is 5, mean deviation score is 5. If I run an independent sample t-test on those deviation scores, it's not going to be different than 0. Then I'm going to reject the null or fail to reject them and say, okay, these are sort of different, right? But if my mean deviation score for my first sample is 35 and the mean deviation score for my other sample is 7, I'm probably going to say, yeah, it looks like these scores are much more variable than these scores, more so than we would expect just based on random sampling stuff. And so what we've got is a violation of a homogeneity of variance. Okay, and if we see that violation of homogeneity of variance, we're going to use a slightly modified t-statistic. Okay, people kind of see what's going on here? What we're doing is we've got a statistical correction for a known and relatively common violation of my underlying assumptions. All right, cool. So violations of my underlying assumptions. And so what we want to do is, again, in applied statistical analyses, we're always going to have violations. Stuff's always going to pop up. What we need to do as good applied statisticians is make a determination on whether or not, or what the relative impact this has on my inference, right? And the nice thing we know is these means-based tests, our t-tests, are pretty robust to a lot of different things. And this is where that Bono article that I'm having you read, it's old, but basically going through and talking about when we have to be concerned about violations and when we can say, hey, we've got violations, but I'm probably going to be okay here, okay? So if I have, what we see from simulation research is that our inferences probably are minimally impacted by homogeneity of violations of homogeneity of variance. If I'm pulling from populations with different variances, assuming I have equal sample sizes, the impact of violations of homogeneity of variance are probably pretty minimal. I probably don't have to worry about them a whole lot. Okay. I also see that my tests are generally robust to non-normality in my observed scores, assuming I have reasonably large samples, and assuming that my distributions are similarly shaped. Okay. So again, Rachel, going back to example of you're looking at self-harm, right? And you're looking at occurrences of self-harm in the past month across individuals with sort of some risk factor and without, or some sort of manipulation or something like that. Probably your measure of self-harm over the past month is going to be skewed, but it's probably going to be skewed the same direction in both samples. And so that's probably going to be sort of an okay thing. What we start to become concerned about is if I'm using small samples, right? And I have in my group sample A, I've got a strong negative skew, and sample B, I've got a strong positive skew. That's when we start to become worried about sort of whether or not our test is going to be robust to this type of thing. Okay. Where we don't get robustness in these tests is when we start doubling down on violations of assumptions, right? If I have my data, my observed data are of different shape and unequal variances, then I start to become concerned about sort of whether or not the inferences that I'm drawing from my tests are reasonable, okay? So this is, again, particularly problematic if I've got skew going in the opposite directions across my group. In one sample, I got my skew pulling it one way. In the other sample, I got my skew pulling me the other way. If I have unequal variance and unequal shape, that starts to become problematic. If I have unequal variance and unequal sample size, again, start to become problematic. Again, if I've got if my larger of the two samples, let's say I've got a sample of 90 and a sample of 15, okay? Huge differences in my sample, right? If the larger sample has a larger variance, I'm concerned that I'm going to have too conservative of a test. Okay. Robert, why might this be?
Because actually, if you do have a larger sample, that does display a higher, or like a wider range of scores. It's likely that your test is sensitive enough to determine what was actually happening.
Yeah. So remember that when I'm calculating my test statistic, I have one. I'm going to calculate a pooled variance estimate, right? And that pooled variance says this is my estimate of the variability across my two samples. And if my larger sample has the higher variability or the higher variance, my larger sample is going to be weighted more heavily than my smaller sample, right? So probably what I've done is I've overestimated the variability of my smaller sample, which means my standard error is going to be too big, which means my test statistic is going to be too small. And so I've got some problems. I have a too conservative a test statistic, right? If we flip it around, if my larger sample has a smaller variance, right? Noticeably smaller variance, once again, the larger sample is going to be weighted more heavily. That pooled estimate is going to be an underestimate of what the actual population variance is in my other group. And so I'm going to have too liberal of a test, because if my pooled variance is smaller, it's going to make my standard error smaller. That's going to make my standard error smaller. It's going to make my test statistic too big, and then I'm going to have bias going the other way. Okay, so when we're coupling unequal samples and unequal variances, we've got some problems here. Okay, if I've got violations of normality and small sample size, okay, again, this is getting back to that distribution of sampling means, or the distribution of sampling means, right? I'm assuming distribution of sample means is going to be relatively normal, so long as either my population, the population from which my sample is being drawn, is normal, or if I've got reasonably sized samples, right? But if I've got really skewed or ugly non-normal data and my samples are pretty small, now all of a sudden I've doubled down on a couple of different things and I'm starting to have some impact. Okay, so this starts to be very important in terms of not just saying, oh, I have a violation here, I have a violation there. And in your screenings, what I'm going to have you do is sort of say, okay, well, this is what you found. That's easy enough, right? That's just walking through some steps and reporting some stuff and describing what you're seeing. The real trick is saying, okay, what are my recommendations? As a consultant, based on what I'm seeing, are we good to move forward with the test? Are we not? What are the potential implications of this? And how do I understand all this? And sort of saying, so if Riley hires me as a statistical consultant for a project, I'm going to go through, I'm going to do a screening. I'm going to say, okay, Riley, here's what we've got. You've got X, Y, and Z. Those things are probably going to be okay. That's not too big of an issue. We probably proceed with this. This other thing, this is more problematic. We're assuming that this is going to, based on the situation, you're likely to have test statistics that are too conservative or too liberal, right? And so we're wanting to take that into account as we're going through and moving forward. Again, we're not saying that we're not going to do it. We're just saying we need to know where the landmines are, what the potential consequences are, and sort of being able to tie that together to draw reasonable inferences from our tests. Though I don't imagine that'll ever happen. Riley, I expect that every of your projects I'm a statistical consultant on, your data is going to be beautiful. It's going to be, I would say, this is the best data I've ever seen. Like, I've never seen data this good. Okay, questions about assumptions and impact and stuff like that. All right, cool. Let's go through, take a break. Again, let's come back. Try and be back by 4:20-ish. We'll get jumped into, Rachel likes that. We're going to jump back into working with SPSS, so have this set open and ready to rock and roll. Okay? All right, folks. We'll see you in a moment.
Sorry.
What's that?
What is like the one that we need to be pulled up? I was going to ask you that.
Yeah. It's the, also, yes, have this for our, whoops, you can't see that. It's the MVA t-test data set, and have that independent sample T screening set open up. Or, excuse me, the handout, this guy right here. So have the screening and sort of the independent, so to have those, these are the handouts we'll be working with. Okay, so it'll be the PSYC 5060 MVA t-test sets. All right, cool. All right, we'll see you all in sort of 8 to 10 minutes. All right. How are we feeling about stuff up to this point? Feeling like we got a handle on some of the issues surrounding t-tests and sort of various sort of assumptions, all of that stuff. Feeling all right with this? Okay. I mean, this may feel a little bit excessive over t-tests. You're like, oh yeah, are they different? Are they not different? But these mean-based tests serve as kind of the foundation of, our classic experimental designs. Knowing what we can and can't say about the effects that we're observing starts to become important. So thanks for sort of attending all this stuff and sort of working through this. Sort of the more you work with it, the more you practice it, get exposure to some of this stuff, the quicker it'll start to snap in. It's hard with a lot of this, particularly with the screening, until you've seen a lot of sets and you've worked through a lot of stuff to know, hey, is this weird or is this not weird? I'll try and help you sort of go through and sort of identify, yeah, this is something to be concerned about, not. But hopefully, so as you go through, it'll get easier as we go through the more of these that you go through and run. Okay. So let's get back into sort of this last push. So what we're going to do is we're going to run an example in SPSS with a small set. And so sort of the build up to this, and again, I've talked with some of you about this, is you're approaching these applied problems, always spend some time with the setup. Make sure that you understand what the data are, what the question is, sort of the issues with that before you jump right in the middle of, never just jump right into the data. I mean, crunching the numbers is fine, but on the back end, you're going to be confused about what you've done and maybe it missed things that don't make sense. So always, whenever you're approaching these, spend some time, read through the introduction carefully, make sure that you understand what the sort of purpose of the study is or what the question is, what the measurements are, how they were collected before you jump in. It will make the extra time you spent will make your life a lot easier. Okay. So here, in this hypothetical example, we're interested in gender differences in marital satisfaction in motor vehicle accident survivors in long-term heterosexual relationships. 22 men and 5 women, 22 women and 5 men meeting diagnostic criteria for PTSD subsequent to motor vehicle trauma completed the Lock-Waldis marital adjustment test. Scores range from 2 to 158. Higher values including greater relationship satisfaction. Participants also completed the Marlowe-Crown Social Desirability Scale to assess differences in tendency towards socially desirable responding in male and female survivors. Based on previous research, investigators hypothesized that women will report greater levels of marital satisfaction than men. Tendency towards socially desirable responding is expected to be similar across groups. Okay, so Allie, what are my 2 outcomes that I'm interested in here?
So the marital adjustment outcome from that test, and then social desirability.
Yeah, and why might I be interested in social desirability here?
That could affect the way that people respond to the test.
Yep. So again, there are better ways to handle this from a statistical standpoint, but what I want to do is if I do see a difference, that I sort of want to see whether or not that difference might be a product of not actual marital satisfaction, but maybe more to do social desirability types of things, right? So as we're going to go through, before we actually jump into all this, what we're going to do and what we'll always do first is go through and run some run a screening. And so how many variables, how many groups, Allie, am I working with here? 2. And how many outcomes? 2. Okay. So we're going to want to go through and sort of make sure we're attending to all of this. And I posted this, I had posted examples, but I hadn't posted this before. This is in your handouts folder. This is a general framework for reporting univariate screening. This is just giving you sort of a basic sketch or a system for reporting or things that you should be looking at for your general screenings, missing values, right? Sort of where these are coming up and how they're popping in, accuracy and plausibility of scores, right? Are the scores that I'm reading consistent? If you worked with, say, lab research with undergraduates or anybody's reporting data or entering data, sometimes you get weird codes that don't make any sense. You want to make sure that you identify those before we jump into actually sort of running analyses. Talking about your univariate distributions, again, for our means-based tests, univariate distributions, we don't have any technical assumptions about our univariate distributions, but we sure want to make sure that we know what's happening in our data before we jump in the middle of it. Looking at outliers, extreme values, variance assumptions, and then any other things that might come up. Okay, so just want you to use kind of this bulleted outline, and then at the end, recommendations. This is just you playing consultant, sort of going through saying, hey, these are the things that are going on. These would be recommendations or things that we should be concerned about, or these are things that came up that aren't great but probably won't impact things, kind of tying it all together. Okay. So for the screening, we're going to work with this independent sample T test, independent sample T screening as we go through. And I'm going to move you all out here and move this in here. All right. It's too early, Pandora. We still got I still have 30 minutes on my clock. It's not time to be done yet. So
I've got this guy here.
I know.
Leave him alone.
All right. So what we've got here in SPSS is our set. We've got our participant number, sex of our participants. We've got a PTSD diagnostic score, which is final, but that's not relevant to what we're doing. CAPS, sort of a continuous PTSD score. That's also not relevant to what we're doing. But here's our Locke-Wallace and our Marlowe-Crown. These are both variables that we're interested in here. If I go down and click on variable view, I'll say here's my variables, here's labels, values, missing, sort of all that stuff. If you haven't gone through, has anybody gone through and worked through that SPSS demo video that I posted? Okay. If you're going to be using SPSS, definitely worth going through to make sure that you're oriented to that type of stuff. I've got some handouts that are posted in the handout folder that are very good. Robert and Allie, I'm sort of doing the similar thing for state. I've been telling you that, but I keep running into kinks about like 20 minutes into the demo, and then I get mad and have to shut down and start over because I have to go back through and fix things. But it will be up there before you jump in the middle of this. So first thing we want to do, based on my general screening, is go through and take a look at missingness in my data. Okay, so with small sets like we're working with here, probably the easiest way to do this is I just go through click on Locke-Wallace, right click, hit sort ascending. We don't need that right now. Okay, so I see that case 132 is missing a Locke-Wallace score. If I do the same thing with my Marlowe-Crown, sort ascending, same thing, 132. What I'm going to do is I'm going to go through File, Save As. I'm going to call this scrap. If you were doing it, you'd probably call it a working set or something like that. Saving it so that you're not working with your original data, because what I'm going to do is I'm going to record somewhere, okay, I've got case 132 that was missing scores on both my outcome variables, and so I would want to make note of that. So I've got one missing value, or one case with missing data. Okay. So now I've gone through and I've got my information, so I've got cases with full data. What I want to do is I'm first going to go through and I'm going to go to data and I'm going to split files. Okay. Because for my screening, do I want to look at the distribution of marital satisfaction and Marlowe-Crowns in my entire sample combined? What do you think, Natalie? No, right? Because is it possible that marital satisfaction and social desirability, the distribution of those scores look very different in men versus women? Yeah. Is it possible that an extreme value for men may be right dead center in sort of what we would expect for women? Yeah. So anytime we're working with these independent sample tests, first thing that you're going to do once you go through and identify, oh, whoops, this is the other thing too, I should have, and I didn't. Well, I did eventually. Here's my screen. Here's my screening. Want to make sure that I'm recording. So I have, eventually I'm going to say missing Locke-Wallace total and Marlowe-Crown for case number 132, and identifying that as one of the women in my sample, just to make sure that I know where my missing data are falling to help me identify patterns and stuff like that. Okay. So, but what we're going to do is, in order to split this file up, what I'm going to do is I'm going to go to data, and then I'm going to down to data split file. Oops. And then I'm going to compare groups. And what's my grouping variable here, Ari? Yeah. I'm going to go down, select that, drop it in. I'm going to split file by group. And then what I'm going to do here is I'm going to go ahead and hit paste, right? And so what I'm going to do, and I would encourage you to do the same, I don't care about this active data set thing, is start to, because I'm going to tell you right now, your screening for this problem is going to follow probably the same number of steps as screening for any problem. So I'm going to say split file by sex here. Okay. So then what I'm going to do is I'm going to run that syntax. What I'm going to see is it's put my men first, my women second, kind of ordered those up. Okay. So as long as I have that split file on, I don't want to do that. As long as I have that split file on, anything that I do, any analysis I run, is going to run that separately for men and for women. Okay. So what I'm going to do now is I'm going to go analyze descriptives. Oops. And I'm going to go to descriptive statistics. Okay. And I'm going to go and I'm going to look at my Locke-Wallace, my Marlowe-Crown. I'm going to save standardized values as variables. I'm going to go to options, request my skew, my kurtosis. I'm going to hit continue here. And now I'm going to go through and paste. Okay. And again, what I've got is descriptives here. Okay. So again, just writing a note to myself to tell me what I'm doing. Okay. So if I go through and I run this, okay, what I'm going to get is it's going to give me my scores separately for men and my scores separately for women. Okay. So now if I'm going through and I'm taking a look at this, first thing I'm going to want to do, maximize this to, okay, is I want to go back through and take a look to make sure that my scores are reasonable. Okay, so if I look at my min and my max, so my Locke-Wallace marital satisfaction scores range from 2 to 158. Okay, Erica, are my scores looking okay for men and women? Are they at least within range?
Yeah, they're within range.
Yeah, they're looking within range. And my Marlowe-Crown 0 to 33. Any problems with my social desirability scores in either one of my groups? No. Looking okay. All right. So wanting to go through and always make sure that my scores are within bounds so I can go through and talk about that. Okay. Erica, let's stick with you. What about looking at skew and kurtosis values? Is there anything that you're seeing in these that would suggest severe violations of normality across scores in men or women here?
No.
Yeah. What are my largest absolute values here?
For which one? Sorry.
For any of them. For my skew and kurtosis values. So where do I have the largest absolute values for skew and kurtosis?
For skew, it would be the 0.913 for the males.
Okay. Oh, so this is your standard error. Ignore that standard error. What you're looking at is your test statistic here.
Okay.
Good.
Right.
Okay. So across skew and kurtosis, thinking about kind of general rule of thumb that means very little, if anything at all. But there are people who say, skewer kurtosis plus or minus or greater than absolute value of 2. Where are we seeing sort of maybe a little bit higher levels?
The kurtosis of the male population.
Kurtosis of the men, right? So that might catch my eye. And that negative kurtosis, one more and I'll leave you alone. That negative kurtosis, what shape does that negative kurtosis imply?
More variability?
Well, remember the kurtosis is always going to underestimate our variability. But are we talking about with negative kurtosis, are we talking flat boxy or peaked with flat tails?
Flat?
Remember, negative is platykurtic, and it's that kind of square, kind of boxy shape. Okay? So, something that might catch our eye here, but anybody else, just from a straight analysis standpoint, Allie, what's the thing that might stand out the most to you in this table? And we already did we know this? No. What's the biggest maybe statistical issue based on this table? Are we happy with the size of that male sample? No, that's garbage, right? So probably what I'm thinking is I've got 5 people in this sample. How often do you get a set of 5 scores that approximate a normal distribution? It's not something that happens, right? So what I would do is I would look at this and I would say, okay, so we have some higher values of negative kurtosis, but I know that negative kurtosis means kind of a boxy kind of shape. I've only got 5 people in this sample. That's probably what's going on with this, right? So I might go through and I might note that we do have sort of higher levels of absolute value of kurtosis here, but looks like at least my scores are all within bounds. So what I'm going to do is I'm going to go through and I've gone through and taken a look at my descriptive statistics. But now what I want to do is maybe go through and take a look at my the shape of my distributions. Okay. Now before in the single sample test, what we had gone through, and gone to graph, gone to chart builder, and used this to go through and build some histograms and box plots, and that's fine. But as we start to get into more complex problems with more variables to go through and deal with, that starts to become a hassle. So what we can do is a shortcut. Now I can go through and I can go to Analyze, go to Descriptive Statistics, and go to Explore. If I click there and I say I want to look at my Lock-Wallace and my Marlowe-Crown. So these are my outcomes that I'm interested in. Okay, but I want to, in this factor list, what SPSS will do is it'll break up these by a grouping variable. So if I go to gender and drop that into my factor list, right, what that's going to do is it's going to give me separate information for men and for women. Okay, so because we're doing a group-based test, this is helpful. And then the last thing, we've got label cases by. If I go to subject number, drop that down here, particularly for when I'm requesting my box plots, any values that are sort of looking at extreme values, what it'll do is it will go through and label those based on the subject number. If you don't put that in, it's going to label it based on the order of the variable, what position that data point is in terms of your file, and that gets to be then. I mean, it's fine. You can go through and track it down and figure out who's who. It's just easier to just go through and put in your participant ID or whatever down in this label cases by. It'll save you some time. Okay. So then I'm going to go to plots, and I'm going to request histogram. I'm going to turn off stem and leaf. Okay. And hit continue, And yeah, we don't need to do anything there. Okay. So then what I'm going to do is I'm going to hit paste. Okay. And if I go to my syntax file, what I'm going to do is I'm going to say requesting M's and box plots by sex. Okay. So that I know what I'm doing here. I'm going to go through and I'm going to go and I'm going to run this. And okay. Looks like it did this correctly. So sometimes what'll happen when you're going through and you're running things, it looks like it fixed this. But I've got a split file on, okay? Because remember, I split my file and said everything that I'm going to do is I'm going to split it up by gender and have it run. But then what I did in that last examine command is it was already split, and I split it again by sex, which will sometimes give you funky stuff. If you go through and you right click and hit sort ascending, or you resort your variable, that's going to turn your split file off. Now that split file is off once you sort, and everything's going to be back to normal. Okay. So what I'm going to do is I'm going to go through, I'm going to sort these data. So they're sorted. So my file's off. I'm back to baseline. Now I'm going to go back through and I'm going to run these data. Yeah, I'm just going to get rid of that and run it again just so I've got a clean thing. Okay. So when you hit explore, what this is going to do is it's going to give you a whole bunch of statistics and descriptives that we've already got. I like requesting it through descriptives. It just kind of streamlines things. But you'll see we get a whole lot more information here through Explore. So this is already the stuff that we need to know we've probably already got. What I want to do is use this to go through and take a look at my histograms. Because what it'll do is it'll produce a histogram for men on Lock Wallace and women on Lock Wallace. And then it's going to give me a box plot where it's plotted these two things together. Okay, so Riley, for my marital satisfaction scores for my men, what is this looking like?
It doesn't look like anything.
It's a pretty flat square distribution, right? It looks like I've got 2 scores at whatever this bin is and 2 scores at whatever this bin is and 1 score. I've got 5 scores. So my distribution is always probably going to be garbage, right? But Erica had noted some negative kurtosis, which indicates kind of a boxy shape. Riley, are you seeing where that's coming from now? Yeah. It's just kind of boxy. And so you've only got 5 people in this sample, so it's really hard to tell what's going on. Riley, are you worried about the distribution of these scores?
No.
No, not really. I mean, it's certainly not normal, right? But it's not terrible, right? I mean, it's 5 scores. It's what we can deal with, right? Now, if we go down through and we take a look at frequency of, or a histogram for our women in our sample in marital satisfaction. Riley, what are you seeing here?
Well, it's more like skewed one way.
Okay. How else might we describe this distribution? I see your finger doing the work. Yeah, what do we call that?
Wait, what?
Yeah, you're doing this. Yeah, what's going on with this? What does it look like is going on?
Would you say bimodal?
Yeah, it looks kind of bimodal, right? Which might make me start, anytime I see a bimodal distribution, I start to worry if my group is actually composed of a couple different groups, right? So, again, maybe a little bit of skew, maybe some bimodal stuff going on here. But again, we've got 21 values, so we're not going to get a really nice looking distribution or a nice looking histogram here, but something I might take note of. Okay. If I go down through and take a look at my box plots, Allie, what am I seeing in my box plots?
Looks like females are generally scoring higher or have higher like median score than males.
Yeah, right. Am I seeing anything that's looking, at least from my box plot, is looking like values that are overly extreme?
Is the 140? I mean, not. Oh no, there's nothing outside the box.
Yeah, right. So my whiskers here are indicating my high and low values for both of these groups, with sort of higher median levels among women as compared to men here, right? So things are looking a-okay here. Same thing for social desirability. Again, I've got, with only 5 values, I've got kind of this boxy distribution that doesn't tell me a whole lot. But again, I've only got 5 values here for men. For women, again, some of that, a little bit of negative skew here-ish. But again, it's really hard to get a good sort of grasp of a distribution with only 20-some scores, right? But Natalie, in these 2 histograms, am I seeing anything that's overly concerning?
I don't think so. Nothing too like
Yeah.
unexpected for the sample size.
Outside of being just small samples, right? I'm not seeing any value that's falling far away from the rest of the distribution that would suggest that it might start dragging things one way or another. Again, with small samples like this is where I start to become more concerned about extreme values. Because if I've got 5 observations and one of them is way the hell out different than the rest of them, that can easily start dragging things around. But here, things are looking reasonable, right? So I'm not too concerned with this. Okay.
Can I ask you a question really quick?
Yep.
Before we get too far away from it, when you asked Erica about the kurtosis stuff, is 2 the value? Can you explain to me again how you know whether it's like bad or terrible or not?
Yeah.
I'm not understanding that.
Know if it's bad or terrible, sort of based on looking at your graph. Okay. Two is sort of what is commonly used as sort of kind of a threshold for starting to say, oh, I've got large kurtosis or a considerable deviation from normality, sort of that type of thing, right? But it all depends on sort of how many people I have, what type of analysis I'm running, things along those lines. What the trap that people fall into is saying, oh, I've got a kurtosis value of 2.1, which means I have severe violations and problems, whereas my value of 1.98 isn't, right? They're not categorically different. You very rarely, if ever, will I have you sort of draw a bright line on a benchmark, something like that. But it's just starting to get you sort of know this is generally what people will talk about in terms of a larger value. But in this case, so we've got kurtosis values that are falling below -2, but they're also based on 5 data points. So I'm going to ignore that and not give that too much credence. Now, if I had 100 people and I had a kurtosis value of, -4, that would be kind of weird, right? But for this, I'm not too concerned with it. Okay. So distributions, if I go through and So if we're going through, taking a look at sort of our output here, do have, again, this is what's nice, I can go through, split my file. So I just go back through, now I split file, rerun my, well, I don't want to do that. So I've got some issues or some higher values of kurtosis in my men, but going through and taking a look at my histograms, I've got kind of boxy stuff for my men just because there's not that many scores in there. For women, I still don't have a big sample there, but those look, there's some stuff I might note, but it's not looking like anything that I need to worry about. Okay. Last thing, at least for what we're doing here, what else should I check before I say that I'm finished up with this? up here I had SPSS save Z values for me. What are we looking at my Z scores for? Anybody remember?
How many standard deviations it is away?
Yeah, looking for potential outliers, right? So I can go down through, and I'm just gonna take my descriptives that I ran up here. Actually, here I won't do that. I'll go through, and I'm gonna go to Analyze Descriptives, Descriptive Statistics, and down to Descriptives. And what I'm going to do is I'm going to get rid of Marlowe Crown. I'm going to get rid of Locke Wallace. I'm not going to save Z-scores on my Z-scores, but what I want to do is I want to get my descriptive characteristics for my Z-scores for Locke Wallace and Marlowe Crown. Okay, I'm going to go to Options. I'm going to shut off Skew and Kurtosis because I don't need those anymore. So I'm just asking for my descriptives for my Z-scores for my Locke Wallace, Z-scores for Marlowe Crown, and I'm going to hit OK. Or excuse me, no, I'm not. I'm going to hit Paste. Okay. And what I'm going to do is I'm going to, just so I don't foul anything up, sort here. Okay. So I'm going to make sure I'm not working with my split file, but I'm going to go through and I'm going to resplit my file by gender. And then I'm going to run my descriptives on my Z-scores here. If I do that, this is what I get. So I've got Z-scores for men, Z-scores for women. You will probably screw this up at some point, or not screw it up, that seems harsh. Make an error in this, right? When we're going through and calculating up here, when we originally ran this, right, we split file and then we calculated our Z-scores independently for men and women, right? And so now, if I go through and I look at Z-scores for men and Z-scores for women, I see the mean Z-score of my men is 0, mean Z-score for my women is 0, standard deviation 1, standard deviation 1. That's how I know I've done this correctly, right? But if I forget to split file before I run those Z-scores, then I'm creating Z-scores based on the full sample, not separately within men and women. And if I were to go through and look at Z-scores independently across these two, I would see some mean that's not exactly 0, some standard deviation not exactly 1, tells me that I've made an error somewhere and that I need to go through and correct that. Okay, but if I go through and I've done this correctly, taking a look at my Z values here, Natalie, do I have any concerns about extreme values in these data? Not from looking at the graphs, no. And what are you basing that conclusion on?
Like the uniformity of the graphs, like there's not, like where the graph is, there's not one that's much farther away.
Okay. Yeah. And so if we're looking graphically, and which is probably where you are going to put the most stock in, so we're not seeing anything that looks too terribly confusing. But Rachel, if I'm looking at the descriptors of my Z-scores, am I seeing any evidence of anything that looks like a problematic value or problematic case there?
No.
Yeah, why not?
The farthest away, it looks like about 2 standard deviations, which is...
Yeah, exactly right. Yeah. If I go down through my, if I'm looking at the absolute value of my Z-scores, the farthest score I have from the mean is for my women. There's a Marlowe Crown score that's about not quite 2 standard deviations below the mean, right? And if I go up here and I sort my Marlowe Crown, so I see among women here is, whoops, that's Locke Wallace. So I've got a woman who scored something that's sort of close to 2 standard deviations below the sample mean, but in the grand scheme of things, I'm probably not too concerned about that, right? Again, if I'm looking up on Marlowe Crown, if I'm looking at this, here's my low score, right? It's not terrible. My low score, terrible. Not terrible. If I were going through and I'm looking at these and I'm seeing Z-scores of particularly in a small sample like this, that start to exceed 3, 4, something like that, that starts to say I've got a score that's several standard deviation units from the mean, and that starts to become more concerning, either above or below. But here we're not looking too bad. Okay, so this covers what we would do in a screening for the write-up. Now we're not completely finished with this because, so we've got screening. I'm noting my missing data for Lark Wallace and Marlowe Crown for case number 132. Accuracy and plausibility, no evidence of problematic values. Remove my missing case, 26 people in the data set. Here I'm talking about my distributions for men, noting the sample size, talking about skew kurtosis for my variables, talking about my histograms and box plots here. Same thing for women, sort of going through and providing just a description of what I'm seeing there. Outliers, extreme values, saying I'm not finding strong evidence of univariate outliers here based on my z-scores. Homogeneity of variance, we'll talk about that when we actually run our statistical test, so hold off on that right now. And then my recommendations, okay? So I'm saying missingness was minimal, design noticeably unbalanced. That's probably the biggest thing I'm looking at. I got way more women than I have in men in this sample. Evidence of strong negative kurtosis, probably the result of a limited sample. Levine's test says possible violation in terms of social desirability. We'll get to that in a moment, or sort of next time, okay? And so then this is just kind of my write-up, kind of talking about sort of what I'm seeing, sort of whether or not it's a problem, things along these lines, kind of summarizing everything. I'm saying analyses of mean comparisons proceed with caution, recognizing that these data likely underestimate variability in marital satisfaction and social desirability, particularly on men. So you got a sample of 5, right? Recommend analysis of differences in social desirability. Also use corrected tests, possible violations of homogeneity of variance. So just kind of going through and kind of tying this stuff together. All right. So this is just to give you kind of an example of how when you're going through and doing this, you might sort of using some structure to tie this stuff up. Again, don't get creative. Don't reinvent the wheel. I actually encourage you not. I love creativity, not with this. This is a nice streamlined way. This will save you time if you kind of use this as sort of a template. I mean, don't cut and paste words, sort of use your own ways to go through and describe sort of what you're seeing. But this should give you some structure for how to run through those screenings. Okay. All right. So that takes us to time. What we'll do is we'll start in next week, and this way we'll for sure knock out, finish up t-tests. That's fine. We'll just kind of take things from there. So still push that next problem set down the road. So you just, and this is nice, give you some time. You don't have to worry about stat assignment right away. But what I would say is this t-test set is pretty big in terms. This is the first set that you're going to be using SPSS and actual data. So get an early start on it, right? Because it'll be more of a chore than sort of the ones that you've done up to this point. So get an early start on it. You've got lots of time, so just sort of chip at this slowly away. So as you're working through, let me know if you're running any questions. Other than that, you guys should be good to go. Yeah. Questions before I turn you loose? Yeah, Natalie.
What was the new due date? Just so I can put in my calendar.
Let me see.
Sorry.
Is it going to be the 30th?
Yeah, I think it's the 30th.
Okay. So yeah, we'll finish up on so it'll be the 30th there. Okay. So lots and lots of time to go through and work on this, but always better to get a head start. It's easy to underestimate. CJ, I right? Easy to underestimate how much time this stuff can take you once you get into it.
Oh yeah, absolutely.
Okay, yeah. So again, part of this when you're actually working with data is sort of like, oh, I think I got it, but then you're actually sort of getting the mix and you're like, wait a minute, I'm confused. Having to get turned around, collaborate with one another, say, I think we should do this, I think we should do that. When you're green and just doing this, like after a while, you'll be able to knock these out, but sort of particularly when you first get started, navigating the programs and stuff like that, you run into hiccups. So just make sure you give yourself enough lead time. Okay.
No one else has to stay for this.
Yeah, go for it. Yeah, and folks, if you need to take off, sort of go. Thank you so much for hanging around. Don't want to sort of keep you here, sort of because I know we're past time. But yes, Brittany, go for it.
I looked at the first one and just like bit number one, right? You're not telling us exactly which t-test to calculate. We have to figure it out, right?
That is correct. Yes.
Okay. Well, I'm not. All right. I'm probably okay. I'd have to read it and figure it out. So
Yep.
but all right. Sounds good.
Okay. So, and I like this too, because this is you sort of going through and saying, okay, what's the question? What are the data I'm using? So, what is the appropriate test for this? Okay. And some of these get a little bit tricky. Have to sort of requiring you to think about it a little bit. So, work through, collaborate together. But if you have questions, definitely chase me down.
Sounds good.
Got it?
Thanks.
No problem.
Bye.
All right, folks. Thank you so much. Again, you're doing great work. CJ and I both thank you for your organization and sort of your efforts on this. Stay after it and let me know if you run into snags.